So now we have the quantum field theory for light, including the Hamiltonian and how things evolve, and we also have a good approximation for how they interact with neutral atoms. So you might think that we have the tools to analyze a simple system like a two-level atom interacting with light. However, what we have here is still a very large quantum mechanical problem. Formally, it has an infinite number of modes and an infinite number of potential photons. And we've already discussed that in order to make it a tractable problem to calculate, we have to reduce that number of modes or that number of photons dramatically. In fact, in quantum optical situations, we usually try and reduce the modes so far we end up with one, or at most a handful. Now, is there a situation physically here when you're dealing with a two-level atom and some light where only one of those optical modes is important? And the answer is yes. What about the situation where most of those modes are in the vacuum, they're empty, but one of those modes has a large number of photons in it? In other words, what if your two-level atom is having a laser shining on it? In that situation, we end up with the simplest possible model we could get, a single optical mode coupled to a single atom, and this is called the Jaynes-Cummings model. Now, the Hilbert space for this system is the tensor product of the two-level atom and a single mode optical field. And so a basis for that is where we have the ground state and n photons, and the excited state and n photons, and all these states for all the possible values of n, all the way up and all the way down to 0. And these are often called the bare states, because if you take away the interaction part of the Hamiltonian, so if we cross that out, then these states, so the bare states, bare of that interaction, they're actually the eigenstates of the system, because they have a definite value of the atomic energy level, so it's definitely G or E, and they have a definite number of photons, so they have a definite energy for the optical field. Now let's see what happens when we turn that interaction term back on. Now this term here connects ground states to excited states, and it also lowers the photon number one. So this term here, that ground state is going to turn to an excited state, and the photon number is going to go down by 1. So it's going to be connected to that. So it's going to send that to there, and nowhere else. Now the other term is going to take excited states down to ground states, and it's going to increase the photon number by 1. So what that's going to do is it's going to go backwards. And so you can see, actually, what we have there is a closed system. That interaction term is just going to couple those two states there. It's also going to couple the next state up here with this one and the state below, and so you've got this big ladder of two states, and so these closed submanifolds are like individual two-level systems. And one of the really nice things about that is that it's very easy to solve the evolution of two-level systems analytically. So let's look at our Hamiltonian acting on this manifold here. So this is the nth Hamiltonian for the nth submanifold. I'm going to do a 2 by 2 matrix because it's an effective two-level state. And for the first one, we're just going to have the energy on Gn. And Gn is going to have h bar omega Ln from this light term. It's going to have nothing from the atomic term. And because the interaction Hamiltonian changes the internal state, that'll give us the off-diagonal term, so we'll get nothing from that. So the other diagonal term is going to give us one less photon's worth of optical energy, but we'll get the atomic energy from the excited state. And then the coupling terms, we're going to get a G, obviously, and when we go from one to the other, we're going to get a root n, and from the other we'll get a root n as well, because A dagger acting on n minus 1 gives us a root n, and A acting on n gives us a root n. So that's the Hamiltonian for that two-level system, and our total Hamiltonian is just a sum of all those different Hamiltonians for our different two-level systems, which are completely isolated from each other. And because it's a two-level system, it's very easy for us to write down the actual eigenstates and the actual eigenenergies and work out the actual unitary operator. Typically, we're most interested in this when the energy of the light is somewhat comparable to the energy difference between the two levels in the atom, because that's when the light has the most effect. And so we often parameterize this in terms of the detuning, which is the difference in frequency between the laser frequency and the atomic energy transition. And we can rewrite the Hamiltonian in terms of that. And you can see that that Hamiltonian is, of course, diagonal when you're on resonance. Resonance is when this detuning is 0. And that's when these two bare states start off with exactly the same energy. And in that case, the energy splits when you turn on the interaction, and you end up with two states that we'll call the dressed states. This is to compare with the bare states, which of course have to be just linear combinations of the other two because it's a two-dimensional subspace. And so when we shine a laser on a two-level atom resonantly, what happens is all these different originally degenerate levels in the manifold split up into pairs. And I've exaggerated the spacing there. In terms of this kind of spacing here, which is about a photon energy. Typically these splittings here are much, much smaller. Now what's going to happen if I actually take a laser and shine it resonantly on a two-level atom? Well, obviously we're going to expect it to excite the atom, and sometimes that laser is going to get the photon when the atom goes back down again, but sometimes that photon is going to spit out into the darkness, into all these other modes here. So remember, we got this approximation by ignoring all the modes that started off in a vacuum, but actually they're still around. And the best way to describe those in a model is to trace over them, to treat them as some kind of environment. So if we go back to what we talked about before in terms of system and environment, if we treat this Jaynes-Cummings model as our system, so we've got our laser mode and our two-level atom as our system, and then all the vacuum mode photon states as the environment, then we can build a master equation. And our master equation, because that Hamiltonian is exactly of the form that we looked at before, our master equation is going to be of a very simple form, where this sigma minus is just the operator that takes us from the excited state down to the ground state. And that curly D is defined. So what does that interaction with the environment do? This part here of the master equation is just the evolution due to the Hamiltonian. It's just the evolution that you get from the Jaynes-Cummings model. So that's fully encapsulated in the eigenstates we describe here. What does this bit do? Well, if we look at what sigma minus does, it takes us from the excited state down to the ground state. And that's exactly what this does. And so unsurprisingly, what it does is it takes anything of state En and puts it into Gn. So it doesn't change the number of photons in the lasing mode. It does change the number of photons in the entire universe. The spontaneous emission term puts that extra photon into one of the old vacuum modes, which then goes off into the darkness, and so we never see it again. And we're approximating that darkness as staying dark. That's the reservoir approximation. And so what this thing does to our Jaynes-Cummings model is it just suddenly takes us from the excited state within photons to the ground state within photons. So I would completely expect spontaneous emission to be taking me from my excited state down to my ground state without affecting my laser. Now the interesting thing about this is that the plus state contains both excited state and ground state. And that's true of the minus state as well. So there's excited state and ground state in all of these dress state levels. And what that means is you can make a transition from plus n to plus n minus 1. Or you can make a transition from minus n to minus n minus 1. And those transitions have exactly the same energy that they used to. So the energy differences are basically exactly the same. So that's the normal photon energy. But you could also make a transition from minus n to plus n minus 1. And that's going to have less energy. Now remember, this scale is extremely exaggerated. And you can also make a transition from plus n to minus n minus 1. So there are actually 3 different energy differences there. You've got these energy differences, which are the normal energy, and you also have this higher frequency photon, and you also have this lower frequency photon. So the question is really, when you shine a laser on resonance onto a single two-level atom, why is it producing 3 different colors? Is that really true?